with Viveka Erlandsen in Bristol. And because I'm always told that I state results I proved or we proved too late, then I'm going to state them immediately in synthetic form. And then we'll come back to them quite later. So the results, the first result that we use, let me call it just proposition A. Let me give nicknames. So this is, so I will not state really the results. I will just say what they're about. So the first proposition we need is standard decomposition of geodesic currents. I will comment later about credits, partial credit, what is known. So for the moment, let me just say just some results. So every geodesic current which I haven't yet defined, C, can be written uniquely as something like this. Okay, so this is the first result. But, okay, so if I don't tell you what it is, this means it can be decomposed in 3 canonical pieces. Then I will tell you 3 disjoint with disjoint supports. And later I will tell you this is a multi-curve, this is a lamination, this is something else. This is mainly a technical thing that we needed. So what are the other results about? So say theorem C. This is orbit closures. So if you have, given a current, so I will define everything later. So a geodesic current describe, so you act with the mapping class group of the surface on the current, and you take the classical, the closure. We'll describe, so you have a group acting on the space of currents, you take the orbit, this is in general not closed, and you describe the closure. So B is a measure classification theorem. Then I will give, of course, a motivation why this is needed. So classification of mapping class group invariant, locally finite, ergodic measures on, this is the space of geodesic currents on S. So there is a complete classification that mirrors and uses also similar results on measured laminations by Lindenstrauss, Mirzaghani, and Hammerstedt. And then there is an analogous for homogeneous. So homogeneous measure classification. So it's the same similar type of classification, but in this case, space of currents has an action of R plus. So we're looking at just homogeneous ones. So we want a classification of ergodic homogeneous. Okay, so this is just the plan. So now I'll go to much back, and I will try some motivation to describe some motivation for why one wants to enter in this technical thing of classifying invariant ergodic measure on some space I didn't define. Okay, so the motivational part will be quite long because I want to explain. So our motivation comes from problem which has become popular, which is curve counting problems. So the setting is the following. So S, let's take S, connected, compact, oriented surface with negative Euler characteristic. For the moment, we will take it without boundary, but later on we will need with boundary. So for the moment, let's keep in this case. And let's fix also H, a hyperbolic metric on S. Okay, so last thing, so if gamma in S is a closed curve, a closed loop, it's a loop, then LH gamma is the H length of the unique geodesic loop homotopic to gamma. Okay, so now I'm going to list some examples of curve counting problems. So let's say example 0. So suppose you are in this situation. You pick a number, a real number, and you define, let me call it CL. This is the set of gamma in S, closed geodesic, such that its length with respect to H is less than capital L. And we call NL the number of such curves. And you want to understand how many of these we have. So, of course, for for a fixed number of L, this can be a difficult problem, but maybe one can say something when L gets bigger and bigger. So, study this function as L goes to infinity. It's quite easy to see that as L goes to infinity, this goes to infinity. So one wants to know how this goes to infinity. And the answer, in this case, is a bit old, so it goes back to early 60s. I think Uber is 61. They show that NL goes as an exponential divided by L. So this n of S is a number that will recur. This is 6g minus 6, where this is the G is the genus. Okay, the genus of the surface. Okay, so this is when I write this symbol, this means, so if we have two functions, f and g, I'm writing this to say that the ratio is bounded. See? Definitely bounded. So this is saying that more or less this number is growing more or less exponentially, very strong. It's, well, the precise asymptotics is a bit, one has to study it, but it's very easily to convince oneself that it should be something like exponential, more or less. So it can't be a polynomial. So this contrasts very much with what happens if one studies the number of simple closed curves which have bounded length. Yeah? I think it is. Let me think. Yeah. Yes, I think so. Yeah, it depends on the entropy. Yeah, it depends. Yeah, there must be the entropy. Yeah. Sorry. Anyway, this number will. Okay. This will keep for later use. Yeah, so here you must have the entropy of the geodesic flow. Okay, so the situation is different though in the simple case. So example 1, same example, but we just changed the number of curves we are counting, the type of curves we are counting. So let's take gamma in S, simple closed geodesic, or simple closed homotopy class of curve is the same. Let's try it this way. Simple closed curve up to homotopy such that the length of gamma is as then L. Here we have added this thing simple. And then again, we want to count how many of these we have. And the situation is very different. So in this case, I think it is due to Rivin that this number goes as L to this power. And later, it was shown by Mirzakhani a more exact asymptotics. Well, 8 is publication. So then she showed really what's the ratio of these two numbers. So more precise. So she computed the ratio. Okay, so in this case, you have a polynomial asymptotics with this power 6g minus 6. Now one can then try to play with all these kind of counting problems. So you can look at different curves. Say, for example, next example, one can try to show, to count curves that have at most 3 self-intersections and see if there are as many as simple curves or if they have an asymptotics like exponential and so on. So that people started investigating all these problems. So let me call this example 1a. Example 1b. So let's fix an integer, non-negative integer, and let's look at the set of curves. Now I won't repeat up to homotopy, so it's just homotopy classes of curves. So these are closed such that the length of gamma is at most L, and we want the curve to have at most k self-intersections. So what does this mean? Let me write it this way. So very, very quick digression for those who don't know. Most people know. So what is the I of gamma gamma? This is the geometric self-intersection, which means is the minimum. So if gamma and gamma prime in S are closed curves, we can define I of gamma gamma prime to be the number, the minimum number, so say minimum of the number of intersections where gamma tilde is homotopy equivalent to gamma, and gamma tilde prime is homotopy equivalent to gamma prime. And this is realized, so this is a geometric intersection number. Section. And this is realized if, for example, two conditions occur. The first one is if gamma and gamma prime are transverse. And the second is that they form no bigon. What does no bigon mean? Means that they're not allowed to do something like this. So if this is gamma prime and this is gamma, you shouldn't see something like this in your surface, because you see that now you would have two extra intersections that you can avoid by pulling gamma prime up and deforming it. So you put them in this position so that they are transverse and they form no bigon. You can always do. You put them in minimal position, and then you have that the intersection is realizes this. Okay, so this is exactly the same. This is automatically satisfied if you take the geodesic representatives. If you take the geodesic representatives, they're always transverse because they're geodesics, and if they are distinct, and they form no bigon by Gauss-Bonnet. So here, this exactly means you take the geodesic representative for gamma, and then you count how many self-intersections it has. Okay, so suppose, going back to the problem, that one wants to count curves with at most k self-intersections and bounded length, and then again want to count this, and this is due, I think, to Sapir. That again, this has the asymptotics the same as in the simple case, with k fixed, of course. If you let k go to infinity, you get all closed curves. So. Okay, just a few more variations of these examples. One C, you can take all, okay, so you can take all curves of certain types. So what does a type mean? So we have what is the mapping class group of S? This is just the group of connected components of the diffeomorphism of S that preserve the orientation. So these are isotopic classes of diffeomorphism of S. So this clearly acts on the set of closed curves. So instead of counting all closed curves, we can count closed curves in an orbit of the mapping class group. So we can fit, for example, we can take a curve which is something like this. And we want to count all curves of this type, which means that they're taken by diffeomorphism to other types of curves. So it can be another type, which is this one. And you want to count only curves of this type. So, for example, you want, so fix a closed gamma 0. And you want to count all gamma in the orbit of gamma 0 that has the property that the length is at most L. And so, again, this number goes as the same L to the n of S. This is due to Erlandsson, Soto, and I think 2015, and Merzacani independently. More or less 16, but years. In with two different proofs. Now, I wanted just to illustrate, okay, I could go on, but I wanted just to illustrate two other counting problems which have a different asymptotics in this case. So let me call it example 2. So we take, again, simple closed curves of length at most L, but we don't want just to count them. We want just to take the sum over all such simple closed curves of something which is not one just counting, but is, for example, a power of their length. So I want to count with weights. And then this is, if one knows the solution of example 1a when counting simple closed curves, then this is not difficult to conclude that this goes as L to the ns plus E, where E is exactly this power. So, okay. We will see later why, but this is very easy. I can leave it as an exercise using 1a. Okay, last example, example 3. So this is, in some sense, is not radically different than example 1a. This is a bit different now. Okay, so to illustrate example 3, let's take a cover of S, a finite cover. I'm drawing one which is not the one I'm interested in, but this one I can draw. Now I've drawn kind of prototype of 2-to-1 cover. And now suppose you have a curve, a closed curve upstairs, something like this. And you push it down. What you get, in general, you get something which is not simple. In this case, you get something like this. That has two intersections. Or, another thing, you can take this curve, you push it down, and you get something like this. But done twice. Okay. So basically, what you get is you can get either a closed curve, which is not necessarily simple, or you could get a multiple of some curve. So basically, when you push down, you get something which is a weighted multicurve. So weighted multicurve is a sum of, say, R plus multiples of closed curves. Usually, actually, one uses the word, very often one uses the word multicurve to say simple, that they never intersect. We use it just to say a sum of curves that can also intersect. So otherwise, we can say just simple multicurves are sums with real coefficients. These are curves such that gamma I is simple and the intersection of gamma j, gamma k is equal to 0. So simple multicurves is just the collection of curves which are simple and disjoint. In this case, a weighted multicurve can be just an arbitrary sum. Okay, so so basically what we see here is that if we push down curves, we get an integral multicurve downstairs. So what is the example of curve counting? I can produce a bizarre problem using covers. But in order to make this problem to be mapping class group invariant, I have to use a nice cover, which is sort of canonical. So let's produce it this way. So let's take the fundamental group of S. We can map it into the, so let's fix some integer, which is at least 2. Let's map it to the homology with coefficients m mod m. So this has cardinality m to the 2g. So the kernel must be of finite index. And actually, this is a characteristic subgroup. Why so? Because it is generated by commutators inside this and mth powers of elements. So it must be invariant under automorphism. So we construct the cover in such a way that this is exactly the fundamental group of S tilde. So this is a cover of degree m to the 2g. And what we can do, we can count curves here which come from simple curves upstairs, for example. So let's take CL. This is, let's call it this way. So gamma, let's call it a multicurve in S, such that gamma is of type P star of a gamma tilde, where gamma tilde is simple upstairs, and the length of gamma tilde with the pullback metric. So here we have a metric, and here we have its pullback. This is less than L. Okay, so now if you try and count this number of curves, the fact is that if you have one such, so the number of curves that give the same curve downstairs can be at most the degree of this. So actually you get something that goes more or less as L to the n of S tilde. But this n of S tilde is bigger than n of S. So actually it can be quite bigger. So here we are counting things which are not necessarily simple, of course. It can be a bit messy. Okay, so this looks a bit different than the other problem. Okay, so now that I've listed all these problems, I wanted to show you why one gets, for example, in the simple case, so there was problem 1a that I just erased, why you get some power like this. So the problem 1a, why we get this type of asymptotics. So kind of informal, more or less a sketchy argument for these asymptotics. So the idea is that you want first to parameterize say simple integral multicurves. Integral, simple, we know what it means. Integral means just that the weights are non-negative integers. Let's call this, for some reason that will be clear later, with this symbol. So how you parameterize? So you can parameterize using results by den, which gives so-called den or den-Thurston coordinates on the sets of simple integral multicurves. So how these are constructed? So you fix a pair of pants decomposition on S. This means that let me draw, you pick disjoint simple closed curves such that the complementary regions are spheres with 3 holes removed, like this. So the pair of pants decomposition is the collection of this alpha 1, alpha 3g minus 3. These are alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, in this case alpha 6. Okay, then if you have a curve or a multi-curve wandering around, then you want to analyze what happens. You chop it, every pair of pants, you want to see what happens inside each pair of pants. So the first piece of information is how does your multi-curve, so let's take it to be a multi-curve, say just for simplicity, but it's not needed, say with weights which are only 1. So we pick a pair of pants. What do we see? We see some curve that enters and goes out. And so the first information is how it intersects the boundaries. So we define some numbers, mi, which is the geometric intersection of gamma with alpha I. Now this is telling us how many of component pieces of gamma are entering. So if this is alpha I, alpha j, alpha k, mi is telling us how many things are entering. But now we want to know also, okay, so now we want to know what is happening inside of the pair of pants. And what we can do is, on every alpha I, let's cut a segment here, here, and here. And let's put mi segments coming in. We put mj, and we put mk things. And now, for each of these, we have to say whether this is joining to something here, or it's going around and coming back to something here. So this is once you have the information. So one thing is that mi plus, because every arc enters and goes out, the sum must be even. So one condition that you immediately get is that this is even, an even integer. The second thing is that it is always possible to, once the sum is even, to connect these things in a canonical way. And the idea is this. The idea is that you have sort of canonical models for these curves. So you can have something that does this, or something that does this, something that does this. Or you can have also something that comes back. like this. For example. Or you can have also the other three. So this is okay, so this, if this is alpha j, alpha I, alpha k, so you have these curves of type ik, jk, you have gamma ij, gamma ik, this is a gamma ii, and then there are of course also gamma jj and gamma kk. So each of these is isotopic to any one of these three types. And once you have this mi and mj, you can canonically realize, so connect this in such a way that they look, each of them looks like in this. The problem is when you want to glue two different pens, so this is telling us what's happening inside the pair of pens. The problem is that once you have two pens that are glued so here we have mi, so suppose this is alpha I, and this is alpha I, and here we have mi coming here and mi going there. Then you might glue them just taking the first to the first, the second to the second, and so on. Or you can shift by one, and you can have the first one go around. So this is this obvious gluing corresponds to zero twist, but you can have, I'm doing twist one. You can have these things, say with three, this can be glued to something which is does this way. So basically this goes. So basically there is a twist parameter here. Okay, so this give more or less this give coordinates on the space of on the set of simple closed curves. And so like simple, say in this for maybe multi-curves, these are sent to some numbers. So gamma is sent to mi and tau I. Sorry? You can have several components, yeah. Okay, so the image is just dictated by this condition, that the sum must be even, and that if mi is equal to 0, for mi equal to 0, tau I is just the number of components of gamma homotopic to alpha I. So this is a non-negative number. So there is an exception how you define tau I. So this condition, that if mi is 0, this is non-negative, and this condition characterize really the image, and this is an injection. So actually you have described, the theorem by then is that you describe the set of simple multi-curves by these numbers. Sorry, the choice of what?
The choice of, so you're saying that if you know your MIs, you just know the number of intersections.
Yeah.
What path
Yeah. Yeah, so you fix a standard pair of pants, and then you fix standard representatives, and then once you know the MIs, you realize this with the standard representatives. And then you produce the twists with respect to those representatives. Okay, so now that you have a parameterization, then you realize that this result that I've seen actually in a paper by Mirzakhani, but I have the suspect that it should be known also before, that the length is of a curve, of multi-curve gamma, is basically given by this. Why? So because in a hyperbolic surface, there are two reasons for a curve to get long. One is that you are passing through a collar around the curve. Another reason is that you have been going under twisting, and then you become longer and longer because you are twisting. So you can define, given the pair of pens and H, you can define a combinatorial length which is basically the absolute values of the twists times L alpha I, because every time you twist, you get more or less longer by this quantity, plus another quantity that depends on this mi, and this col is the length, the width of a collar, hyperbolic collar, with core of length L of alpha I. So the picture is this. If you have alpha I, then you have something like this, and then you have a standard collar. And this is the width. This collar depends only on the length of this curve. So this is a function that depends only on this. It has, well, actually, this is a bit of a strange function, but it's this one. This is the width of the collar. So whatever, you can see that after you fix the pair of pens and H, this number is fixed, this number is fixed. So basically, you are just computing the sum with coefficients of the absolute values of the TIs and absolute values of MIs. So basically, the result that I told you I've seen in Mirzakhani is that this quantity is more or less the length up to a factor. So it means that if you want to count curves of certain length, then you can count curves of certain combinatorial length. And curves of certain combinatorial length are curves that sit in a ball inside this space. A ball for an L1 norm, because you see that the coordinates are Ti and Mi. These are just coefficients. So you're asking for things which are in a ball of radius L. So basically, you're counting inside this space with a certain L1 norm. Inside this space, you are counting integral points inside the ball. And so these grow with the right power. OK, so I used a lot of time on this, but this was, to me, was quite interesting. So how you put truly what is something like this? So how do you put multi-curves inside something, some meaningful? Here, this has no geometric meaning, not at the moment. So it's just some space that I cooked up, just completing this tensoring with R. So, but if I want to see really these multi-curves as integral points inside some space, what do I do? So this was the construction by Thurston. So you can embed multi-curves. OK, so we have this, which I told you these are integral multi-curves. So with integral weights. First thing I can do is that I can put them inside real multi-curves. one can think, well, this is already completion. Well, it's not, because if you are in Rn and you take integral points and then you take rays, this is not the completion of. So if you want really to complete it, what you do, you embed this inside the bigger space, space of maps from simple closed curves to R. So you take a real multicurve, we call it J, and you send it to the map that takes gamma to the intersection of gamma with this. So this quantity is just defined by linearity. So this is the sum of A, J, intersection of gamma, J, gamma. So you embed this inside this huge space of maps, which has a topology, and then you take the closure. So this is one definition. So what sits in the closure? So in the closure, you see some limiting objects, which are measured laminations. And what are measured laminations? These are, so just a lamination or a geodesic lamination is a closed subset which is foliated by complete geodesics. So basically, a simple closed curve, simple closed geodesic is a geodesic lamination. Yes, this leaf, which has a complete geodesic. Or two disjoint geodesics are a geodesic lamination. And two geodesics that intersect do not form a lamination because this cannot be foliated. I mean, the two leaves would intersect. And measured geodesic lamination means that you have a transverse measure. So you can assign a number to every transverse arc. So lambda, so measured geodesic lamination is a geodesic lamination plus a transverse measure. So a weighted, these real multicurves are measured geodesic laminations because the curves themselves, when you take the geodesic representatives, are geodesic laminations, and the real number gives the weight for the transverse measure. So every time you cross a component gamma j, here there is a weight aj, then the measure gives you the price aj. So this basically, describes the closure of this space. So why I wanted to introduce this, because now one can rephrase problem 1a. So remember, problem 1a was counting simple closed curves. Now, how do we want to count simple closed curves? We want to see these curves as integral points inside this space. Now, to see this as integral points, we must, and also we want to see that this is a manifold of dimension 6g minus 6, so that we have a situation like in dense estimates. So to see that this is a manifold and that those ones are integral points, you pick a chart, and you see that this is a manifold, and that in the chart, the simple closed curves correspond to integral points. So how the charts were constructed by Thurston, and they are sort of variation of these then Thurston charts. So charts for ML of S. So you do something of this type. You have your surface, and then you take something which is called a train track, which I will draw wrongly, certainly. This tau. What is this tau? So this is a subset of S, which is a one-dimensional CW complex. It has smooth edges. This is the set of edges, EI. And at the vertices, let's say that it has trivalent vertices. But the vertices are not the way you imagine. Usually you draw graphs such way that the three edges come like this. Here they are different. Here they have the same tangent line. So the three edges coming at the vertex are of this type. So they draw so we have, say, EI, EJ, EK. So these vertices are also called sometimes switches. And what are these train track good for? So I'm going to give you the coordinates for a subset of measured laminations. So the coordinates are obtained giving weights to each of these edges so that you can thicken to something that is a transverse measure. So the set of weights is you take maps from the set of edges to R, and you ask that for every switch we have the condition that the two switches on one side have weights that add up to the weight on the other side. So if you take the train track to be smart enough and good enough, this, so for good tau, this is a domain of dimension, exactly the dimension you want. So it is not something thinner. It's something of the right dimension. And this gives a chart inside the space of measured laminations. How do you construct a measured lamination starting from a set of weights? So you thicken each of the edges. So if you have EI, then you thicken EI so that this one has height WI. So you make a strip and you put a measure, a vertical measure of height WI. And if you have a switch, you see that you get this kind of figure where this has height Wi, this has height Wj, this has height Wk. What you get in the end by thickening this train track, you get a partial foliation, so a foliation of a subset of the surface, which has also this transverse measure. Now, once you have this partial So the partial foliation is on a thickened part of the train track. Once you have this measure on this partial foliation, you can straighten these curves. So to each curve, to each leaf of this foliation, you can associate a geodesic leaf by straightening them, and this gives you the set of leaves gives you the geodesic lamination, and the measure you add on these leaves give you the measure on the geodesic lamination. So this gives this map. Now you can check that if you take integral weights, instead of putting just a measure, in each of these strips, if you have weight 5, you can put just 5 strands. And if you have here weight 2 and here weight 3 and then 5, then you can have something like this. And then if you glue all these blocks, then you get a multi-curve. So integral weights in this chart correspond to some simple multi-curves. So thus we have realized integral multi-curves as integral points inside the space of measured laminations, which is, using these charts, a manifold, a PL manifold actually, of the measure n of L, n of S. Okay, so so this is somehow gives a sort of framework, more organic framework to the situation we had in Den's theorem, where we had these integral points, but we didn't know inside what. Last thing about this train track is that these charts allow us also to give a standard volume form on this space. So you see that here we have these quantities Wi. So for every switch, sigma, we can take the two edges which are on the same side, and we can define omega sigma to be dwj wedge dwk, and then we can take omega to be the sum over all the switches. So this is a closed to form on this. On this tau, and this gives, one can check that this gives a volume form. If you take omega, maybe divided by some factorial, doesn't matter, this is a volume form on W tau. And the thing is that both this symplectic form and this volume form glue if we change charts. So this gives a symplectic structure, but actually a volume. We're interested more in the volume form on ML. This gives so a measure in particular, volume form on ML, and this is what we call Tarsen measure. So let me okay, so why I wanted to introduce this description, because now I said we want to rephrase this curve counting problem. Okay, so let's rephrase in 1A. Okay, so let's take the following measures. Sum over gamma simple in S, so a simple closed curve. Let's take the delta measure over gamma divided by L. So want to define measures on ML. So we're speaking of measures on this manifold. So gamma is a simple curve, so this gives a point here, but also gamma divided by L, so we weight 1 over L, is a point here. So we pick the delta measure centered at this curve. We take the sum over all simple closed curves in S, and actually we divide by this power. So this is a locally finite measure on ML of S. And you can see, because we are taking the sum over all simple closed curve, this is also mapping class group invariant. So why one is interested in this measure? But we were interested actually in counting the number of these curves which were shorter than L. This actually agrees with the measure of the unit ball. So let me call BH1. This is the set of laminations such that the length. So I didn't say we define the length of multi-curves, but then because that's the closure, then the length function extends also to laminations. So one can define to measure the lamination. So you have this unit ball, which is a closed compact subset of this manifold here. And if you take the measure of this, you are just counting. You see, if you're taking this, you are taking the sum over the simple, beside this factor, which is here. You are counting the number of simple closed curves such that the length of gamma divided by L is smaller than 1. So this is counted the same as counting the curve such that the length of gamma is less than capital L. So that's exactly this number. This because we are summing over all simple closed curves. Here there is, so one important point in this construction, you see that in this measure, the H is not coming in. The metric, the hyperbolic metric, is not coming in. It's something just topological of the surface. The metric is coming in when you define this. So it's coming in this, here. So basically, you can rewrite this in many ways. You can rewrite this, as you wish. So then you see that this is fixed once you fix H. And if you want to know the asymptotics for large L, you want to study the asymptotics of these measures. So basically, what you want to understand is measures which are locally finite, mapping class group invariant on ML. So measures, so understand measures which are locally finite and mapping class group invariant on ML of S. And this is exactly what Lindenstrauss and Mirzacani did. And also Mirzacani and also Hammerstedt with a minor difference. So they classified ergodic invariant locally finite measures on these spaces. So what's if you are going to do, now I don't describe it again, but if you're going to study curves which are not necessarily simple, so these do not belong to ML. So you have to build a different, maybe larger space in which these curves, non-simple curves, sit in. And then you want to study something like this, and convergence of measures. What is this larger space? Now you have two ways. One way, which is more recent, is try to generalize this picture. So instead of having these train tracks embedded in the surface, you deal with train tracks, sort of train tracks, immersed in the surface. That this is suited for parameterizing curves and sort of measured lamination curves and currents that self-intersect finite number of times. This is what Erlandsson and Soto did, generalizing this picture. Otherwise, you can use a more abstract thing and generalize this, which I deleted, the construction of ML that I showed at the beginning, so embedding the real multicurves inside some bigger space. Instead of taking real simple multicurves in the bigger space, you take just real multicurves. You complete, and what you get is the space of geodesic currents. This is sort of completion of the space of real, not necessarily simple, multicurves. Now, this space is much uglier, maybe, than what can expect. So this is an infinite dimensional thing. So there are a lot of stuff inside this space. Example, you can take, say, order simple closed curves gamma k by h length. So we start from the shortest ones and then we order them. And then we can take a sum with a very huge, very decreasing coefficient of this gamma k. So this is an infinite sum of simple closed curves with a very fast decaying weight. And of course, all these curves will intersect with each other, even though each one is simple. And then this one is also a geodesic current, which is maybe a bit messy. So you have this huge space, which has some good properties. So it is locally compact. It's infinite dimensional, but it's locally compact, and it is completely meterizable. It is second countable. So there are some good properties. And then if you want to mimic this approach, then you want to study this type of measures on that space, on the space of geodesic currents. So now let me restate the results. So I will not state Lindenstrauss-Mirzaghani because it's included in ours formally. So I will tell you what the result is about. But now let me state formally the results. So we said the proposition A, the standard decomposition. So every current now S can have boundary. Why we need this? Because the proof goes also, in the end, some proofs go by induction with shopping, so you need surfaces with boundary. So every current can be uniquely written as C equal to lambda plus gamma plus alpha, where lambda, okay, let me call C is the support of gamma, A is the hull of alpha, and R is the hull of lambda. So what is the support? We know what the support is. So this will be a multi-curve. So this support is just a union of curves. These are two other currents. So the hull is just the smallest subsurface up to isotopy that contains the support. So this is well defined. So the properties that we want in this decomposition is that C, R, and A are isotopically disjoint. The second is that gamma is a simple multicurve. lambda is an, let me write SCC-free lamination. So this is a measured lamination. SCC-free means that there are no closed leaves, no components which are simple closed curves, because we have put all simple closed curves inside this, this gamma. So here there are no simple closed curves. And alpha is, we can describe it in two ways. One way is that this is an alaminational current, which means no components. Connected component is a lamination. This is equivalent to say that alpha binds its hull. So its hull is a subsurface that contains alpha, and binds means that alpha meets all geodesics inside this hull, which are non-peripheral. So it's really, it feels in a stronger sense. This is different. So if you have, say, maximal lamination in a surface, this is not binding, because the maximal lamination does not intersect itself. So this is not binding in this stronger sense. So this binds really means meets every, not closed geodesics, every geodesics, which is non-peripheral. And actually, okay. Okay, so this is a kind of technical tool that we use. It's not difficult. And let me describe the measure, or maybe theorem C is easier. So the orbit closure. So we take a current and we write it this way. And we want to know the closure of this under the action of the mapping class group. So the mapping class group acts on the set of multi-curves and so on. So by extension, it acts also on this space and this completion, which I haven't described, but these ones are, if you take S, you take the unit tangent bundle for some metric. This is, you take measures on the unit tangent bundle, which are invariant under the geodesic flow. So basically, these are measures on the space of geodesics on the surface. So you have the action of the mapping class group on this C, and this can be this orbit, can be, of course, a mess, but then we want to see what's the closure. This is, we take gamma plus alpha plus a subspace of the space of measured laminations, and then we take the orbit, not the orbit closure. So what is this MLR? So if R is a subsurface, or where R, I didn't tell you what R is and where R is the union of components, is a subsurface which is a union of connected components of S. We remove the supports of these two. So we remove this multi-curve and we remove this hull of alpha. We get chunks of the surface. We take all components that meet the support of lambda. And what is this MLR? Well, we have measured laminations on the subsurface R. I take just the ones compactly supported, so they don't have weights on the boundaries. And then this one injects inside measured laminations on S. So the image is exactly this. So these are measured laminations which are supported on the subsurface R, but not on the boundaries. So the boundaries, there is no weight. So basically, you have this locus of measured lamination. You translate by these two measures, and then you start sending it around with the mapping class group. And this is already closed. So this is the closure of this. If you remove this alpha, this is exactly Lindenstrauss-Mirzacani result. On the orbit closures. And also the measure classification is a bit similar to theirs. And in fact, our proof in the end uses theirs. So it's an elaboration of theirs. It's not an independent proof. So what are the invariant measures? So we more or less perform the same construction as theirs. So I need, sorry, just a tiny definition. So a couple RC is, we call as they did more or less a complete pair if R is a subsurface, C is a current of type gamma plus alpha, so there is no lamination, no lambda, and the support is this, and the support is disjoint. But we also want another condition, is that R is a union of components of the surface S when we remove, again, CNA. Is a union of some of these components. So one can construct some measures out of a complete pair. So this is basically, we take, this is the translate of Thurston measure. On C plus MLR. So this space carries a Thurston measure. Then the image carries a Thurston measure. Then its translate carries a Thurston measure. So this is just the Thurston measure on this translate. Then if we want to make it a mapping class group invariant, then we take the sum. This is the sum over R prime C prime, which is in the orbit of RC under the action of the mapping class group. And then we add all of this. So theorem B is that mapping class group invariant, ergodic, locally finite measures are of this type. Measures on the space of laminations are of this type, up to multiples. And I have 1 minute to say, so again, if if alpha is 0, this is a Lindenstrauss-Mirzaghani result. And for measures on ML. Here it's for measures on C. And then last variation on in the homogeneous case. Why I'm speaking, I didn't say in the homogeneous case, because the measures ML that we consider, they are not homogeneous, they're just sum of deltas. But when you take the limit, you get something which is homogeneous. So if one is interested in curve counting, maybe one is interested, rather than in classifying just ergodic measures, in classifying ergodic measure with some homogeneity. So with that homogeneity, we get more or less the same results. So theorem D, so mapping class group invariant, ergodic, D-homogeneous, locally finite measures on the space of currents are of type, of this type. I put this D. This is again the sum over all. I make it its mapping class group invariant by adding these homogeneous measures, and this is just the homogenized measure. So this is the integral 0 to infinity t to the d minus n of r of the measure r tc dt. So this is just the explicit formula to say I take this measure, mrc, the non-homogeneous one, and then I make it homogeneous along this ray. So just integrate it to make it homogeneous. And then they're all of this type. But in particular, the result is that there is only one. So all the homogeneities are greater than n of s. So Lindenstrauss and Mezzacani already showed that they are at least of homogeneity n of s. What we show is that there is only one which has homogeneity exactly n of s, which is Thurston's. So for d at most n of s, the only one is Thurston's measure. So all the others have greater homogeneity. So as a consequence, if one has a counting problem that goes polynomially with this power, then you know that in the limit, if you take the limit of those measures, then you get exactly a multiple of Thurston's measure. That's why in many problems there is this homogeneity. You will always get, in the end, that everything depends on Thurston's measure. OK, thank you.